Let's take a look at an example of how to use the trapezoidal rule to approximate the area under the curve of the function 1 divided by the quantity 16 plus x squared on the interval from 0 to 2. And we're going to use 6 subintervals to do that. Let's take a look at what we're trying to do by looking at the graph. So here is the graph of the function, 1 divided by the quantity 16 plus x squared. We are doing this on the interval from 0 to 2, and since we are using 6 subintervals to approximate this area, you can see the tick marks that are going to mark the beginning and end of each of our trapezoids. The first trapezoid then, for instance, will end right here, almost rectangular. And you'll recall that we can determine the height of each of these trapezoids with the little formula b minus a over n, where n is the number of subintervals. So applying that here, we obtain that each trapezoid is 1/3 high, which makes sense based upon how our graph is set up. The second trapezoid would end right here at 2/3. The third would end at 1, and so on and so forth. So let's go ahead and set up our rule that we're going to use. Recall that the trapezoidal rule only provides you with an approximation of the integral of the area under the curve. Therefore, use of your approximately equal to symbol is necessary. Please don't forget that. If you think about how you find the area of a trapezoid, that's really where the trapezoidal rule comes from itself. Area of a trapezoid is given to us by 1/2 the height times the sum of the bases. So that's why with the trapezoidal rule here in the calculus, we have a half. Then we need to multiply by the height of each of those, which we just determined to be 1/3. If you take a look at the graph again, remember that height is really this horizontal distance. You almost have to look at these with your head turned sideways to the left. So the height is really that horizontal distance. Remember also, and this is important, in the trapezoidal rule, the trapezoids are all of the same height. It is very possible you are going to come across problems in which you are simply asked to find a trapezoidal approximation, and perhaps the data they provide you with yields trapezoids that are not the same height. That is very possible. In the trapezoidal rule itself, though, the pure trapezoidal rule, these trapezoids all have the same height. Please do remember that. As we proceed from there then, remember that we need the length of the bases, which is really these vertical heights that form, in this case, this would be the bottom base of the first trapezoid, but the top base of the second. Here at 2/3, this length would be the bottom base of the second trapezoid, yet the top base of the third. So you might remember that's why each of these in the middle here, this one and this one, all have to be doubled because they serve two purposes. It's the bottom base of one trapezoid and the top base of another, so it gets double counted for that reason. The bases that occur at x equals 0 and x equals 2, however, simply count once. So the way in which we're going to write this up, we need the function value at 0. That's going to be the length of that very first base of the first trapezoid, plus now we have to start multiplying by 2. And as we've seen, we are going to evaluate this by using our graphing calculator and the built-in functions that it includes. So let's go ahead and switch to our graphing calculator and go ahead and do that. You'll need to have under y equals the function itself, 1 divided by the quantity 16 plus x squared. Please don't forget your parentheses around the denominator. And then you can go to your quit screen and we'll go ahead and type out that which we had in the square brackets. Remember that we're using our built-in function notation. So if you hit vars, go across the top to y vars, into function, it's under y1 that we have our equation. So we'll bring that up, and our first one we need is y1 of 0. Remember, that's telling the calculator that it needs to calculate the function value you have under y1 at 0. Now we just continue on from there, but remember we need to do 2 times the next several ones. So we have 2 times the function value now at 1/3 plus 2 times the function value at 2/3 plus 2 times the function value at 1 plus 2 times the function value at 4/3 plus 2 times the function value at 5/3. And finally, the last one we only need once. That's the end of the last trapezoid, the bottom base of that last trapezoid, at which we need the function value at 2. So if you hit enter after you have that typed in, hopefully this is what you get. Now don't forget though, we have to multiply by a half according to the trapezoidal rule, as well as the height of each of those individual trapezoids, which is going to be 1/3. So in the end, what we obtain for our approximation of this integral is approximately 0.116.